Let's now consider free fermions obeying the Dirac-Lagrangian. Again, in canonical quantization, what we need to do is to find the classical equation of motion using Euler-Lagrange, and then require the field to become an operator because it does not commute anymore with its canonical conjugate. So we get the Dirac equation for a free fermion operator. The solution to the Dirac equation exhibits similarities with the solution for the Klein-Gordon equation. There are a few differences though. There is no square root of omega k in the denominator anymore. This can be understood from dimensions because we can infer from the Klein-Gordon Lagrangian that scalar field has a dimension of an energy, and from the Dirac Lagrangian we can infer that the fermionic field has a dimension of an energy to the power of 3/2. The 1/2 difference is carried by the square root of omega k. Another difference is that the fermionic field solution of the Dirac equation is not Hermitian, and therefore we cannot take A dagger. We have to replace by B dagger, meaning that we will have particles and antiparticles. Also, the Dirac field is a 4-spinor, therefore the operators A and B also have to be 4-spinors. We can use the same procedure as for the Klein-Gordon field. We can get the Hamiltonian starting from the Dirac-Lagrangian and using the expression from Noether's theorem, and eventually what we get at the end is something like. We can get to this result without invoking yet the commutators between say B and B dagger. But if we use this expression, we see that we can rewrite the B dagger term, which is clearly a catastrophe because this means that we will actually gain energy by adding more and more antiparticles. And that's due to the minus sign in front of the B dagger B, meaning that we have a kind of an inverted harmonic oscillator. Therefore, there is no ground state and the theory is not stable, it's not acceptable. So we have no choice but to require another quantization relationship for the commutators between B and B dagger. And in fact, what makes sense to use then is an anti-commutator instead of a commutator. And of course, if we do that for the antiparticles, we have to do that for the particles as well. The fact that we have to replace commutators by anti-commutators for the A's and the B's means that we need also to do the same for the field and its canonical momentum conjugate. By using these anti-commutators, we obtain for the antiparticles also a harmonic oscillator potential with a ground state. It is also interesting to look at what happens when we take k equal k dash in one of these commutators. And this is just a manifestation of the Pauli principle because it means we can't put two fermions in the same quantum state. Again, this is not as general as the spin statistic theorem because what we did was only for the free scalar field, spin 0, and for free Dirac field, so we would have in principle to do that for all spin, all type of Lagrangian with and without interaction, etc. Nevertheless, it's satisfactory to see that the spin statistic theorem ensures that we have a ground state in our theory. And the way the spin statistic theorem is expressed in canonical quantization is that we have to use commutators for bosons, which are integer spins, and we have to use anti-commutators for fermionic fields, which are half-integer spin. So let's look now at the vacuum energy. So we see that in both cases the energy of the vacuum diverge. However, we also see that they have an opposite sign, and there is this theory which we call supersymmetry, and which assumes that for each fermionic field there is also a bosonic field. And if it was the case, that will have the nice property to cancel the infinites of the vacuum energy between fermions and bosons. But there is still no experimental proof of this supersymmetry, so for the moment it's just a theoretical hypothesis.